You know, we all use the internet every single day, but we almost never think about the engine that makes it all run. It's called TCP, the Transmission Control Protocol. It's kind of the hidden workhorse that keeps our entire digital world turning. But what happens when that engine has a few secret flaws? It's a pretty wild question, right? Because for the most part, TCP is incredibly reliable. I mean, its whole job is to make sure everything gets where it's supposed to go. But it turns out there are a few hidden quirks, some defaults that were set decades ago, and even some subtle bugs that have been creating these performance bottlenecks. And it took some really brilliant detective work to solve them.
All right, so before we dive into the case files and look at its flaws, let's give TCP the credit it deserves. Think of it like the engine in your car. You just turn the key, and you expect it to work, right? It gets you from point A to point B without losing any pieces along the way. Well, that's TCP for the internet. Its entire job is to give us a reliable, ordered stream of data. So when you load a web page, TCP is the thing making sure all the different parts, the text, the images, the code, all arrive in the right order and get put together perfectly. It's the protocol that takes internet chaos and turns it into something that makes sense. But here's the catch. That same reliability comes with some built-in rules that, on the modern, high-speed internet, can actually slow things down. So today, we're going to be detectives. We're opening up 3 case files on the hidden flaws of TCP and the super clever fixes that make your internet experience a whole lot better. So our first case file is something I like to call the handshake tax. And yeah, it's just what it sounds like. Every single time you make a new connection to a website, you have to pay a little penalty in time. And believe me, that penalty can add up fast. Okay, so here's how it works. Before your browser can even ask for data, it has to do this thing called a 3-way handshake. It's like a polite but totally mandatory little conversation. Your computer sends a packet, a SYN packet, that says, "Hey, I'd like to connect." The server then responds with SYN-ACK, saying, "Okay, I got your request." And finally, your computer sends an ACK, saying, "Awesome, I acknowledge your acknowledgement." Only then, only after all that, can you actually start sending data. So the key takeaway here is that this whole conversation adds an entire round trip of delay before anything useful even happens. Now, for just one connection, that might not seem like a big deal. But modern web pages, they're made of dozens, sometimes hundreds of little objects, and each one might need a new connection and a new handshake. You're basically paying that time tax over and over and over again. So what does this actually look like in the real world? Well, take a look at this data from Google. It shows that for new connections to services like image search or map tiles, the handshake latency can be more than a quarter of the total request time. That is a huge performance hit, just from saying hello. So the fix for this is a really clever mechanism called TCP Fast Open, or TFO. Just look at this diagram. The first time you connect, you do the normal handshake, but the server also gives you this small cryptographic cookie. Then, on your next visit, you can send that cookie along with your data request in the very first packet. The server recognizes the cookie, knows you're legit, and boom, you get to skip that entire first round trip. 41%. Yep, that means we can make some web pages load almost twice as fast, especially in high latency situations, like when you're on a mobile network. A 41% improvement, just by getting rid of one round trip. It's a simple, elegant fix to a problem that's decades old. Case 1 closed. Okay, let's move on to our next case file. And honestly, this one is even more shocking. We're calling it the 15-minute wait. And it's all about what happens when a connection doesn't just start slow, but breaks completely. Just think about it for a second. You're using an app, and suddenly it freezes up. The network connection was cut. Maybe you walked out of a Wi-Fi range or something. So how long should your phone wait trying to reconnect before it finally gives up and tells you, "Sorry, connection lost"? A few seconds? Maybe 30 seconds?
How about 924.6 seconds?
No, that is not a typo. By default, the Linux kernel, which, by the way, powers a huge chunk of the internet servers and all Android phones, will wait over 15 minutes before it officially tells your app that a TCP connection is dead. For you, the user, that means 15 minutes of a frozen app, a spinning wheel of death, with absolutely no feedback. It is an eternity in digital time.
So why on earth is the default so ridiculously long? Well, it's a combination of two things. First, the kernel is set up to retry sending a packet 15 times before it gives up. Second, it uses this strategy called exponential backoff, which means it waits longer and longer between each retry. The first wait is just 200 milliseconds, but it grows really fast, and when you add up all those waiting periods, you get that staggering 15-minute total. Now, the fix is simple. System administrators can just tune this value to something much more reasonable, like 60 seconds. It's an easy fix, but it really shows how one single overlooked default can have a massive impact on user experience.
All right, our final case file is definitely the most complex. It's a really subtle bug deep in the Linux kernel that was uncovered by engineers at Cloudflare. It's a bug that was causing servers to use up huge, completely uncontrolled amounts of memory. We're calling this one the runaway buffer. So here's the problem in a nutshell. Think of every TCP connection like a glass being filled with data. That glass is a little piece of server memory called a receive buffer. Now, there's a system called auto-tuning that's supposed to stop the flow when the glass is full. But Cloudflare found a bug where the tap would just keep running, letting the glass overflow and potentially flooding the entire server with data it just couldn't handle. And this gets us to the core dilemma. When that glass, the receive buffer, is almost full, the kernel has a choice to make. Option 1, the old buggy logic, was to just let the advertised window, that's the amount of data it's willing to accept, to keep growing. It was basically ignoring the memory limit just to keep things from pausing. Option 2, the correct way, is to shrink the window, to tell the sender, hey, stop sending for a second, I'm full. That's how you enforce the memory limit. And this graph right here shows the bug in action. See those two lines? They're the allocated memory and the memory limit. They are supposed to be separate, with the allocated memory staying below the limit. But instead, you can see them just growing together completely unchecked all the way up to the system's maximum. This is the very definition of a runaway process. And here is the fix. After the patch from Cloudflare, that memory limit is a flat, respected line. The allocated memory grows right up until it hits that limit, and then it stops, because the kernel is now correctly telling the sender to pause. This is stable, predictable behavior, and it's what prevents a single faulty connection from taking down an entire server. So after digging into these three very different case files, what have we learned? Well, we've seen how the internet's most fundamental protocol isn't some static piece of code set in stone. It's something that is constantly being tuned up, refined, and improved. Let's just do a quick recap. We had the handshake tax, right? A built-in delay that was fixed with that clever TCP fast open cookie. Then we had the absolutely insane 15-minute wait, a legacy default value that can be fixed with just a simple configuration change. And finally, the runaway buffer, a deep logic bug that was hunky down and fixed by enforcing proper window shrinking. Each one of these fixes makes the internet a little faster, a little more reliable, and a little more robust. It's a great reminder that this digital world we all rely on is built and maintained by engineers who are constantly tuning the engine, finding these hidden flaws, and building a better internet for all of us, one fix at a time. Which really makes you wonder, what other hidden bugs are being fixed right now, silently making our digital lives just a little bit better?